Hey guys, we are here today to talk about section 7.6 from our textbook, which is on rational exponents. And we've seen kind of how rational exponents in radical form are interchangeable and how you can write one the same way as the other. And that's what we're going to start with today. But the story actually goes a lot deeper. And much of what we'll spend today on is how do we simplify expressions with rational exponents? What are some rules we follow? What are some common themes and ways to simplify? And we'll just work a lot of problems and hopefully get some good practice at this. So looking at the screen right now, we've already introduced this idea of radical form and rational exponents or exponential form. And back when we first saw this, sorry, I'm going to write it with a different variable. One of the things we said was that if we have a rational exponent, x to the a over bth power, then we could just as easily write that as the bth root of x to the eighth, right? And so we kind of said, okay, so whatever power is inside the radical is our numerator in our rational exponent. Whatever power is the root, the index of what kind of root we're taking, that is the denominator of our rational exponent. So the bth root of x to the eighth power equals x to the a over bth. So looking at some of these, just rocking through a couple of them, the fifth root of a. Well, the big thing to remember here is that there's a little invisible 1 here. A to the first is still just a, so oftentimes we don't write that 1. So how would this look in exponential form? A to the 1/5 power. A to the inside over outside, the power over the root index. So a to the 1/5 power. The second one I chose kind of intentionally. It's a square root, which there's no 2 written here for the index, but there's no anything written there for the index, so it is assumed to be a 2. And one of the things that we said then is, okay, if it's assumed to be a 2, that's fine. Square roots are probably the most common, so we don't always like to write them. But make sure that we are using parentheses. We saw an example of this in the notes before. 2ab to the, it's all to the first, and there's an invisible 2 there, to the 1/2 power, 2ab to the 1/2 power. And this is something that I will ask you guys to kind of know and maybe memorize, that the 1/2 power is the same as a square root. If you memorize that, it'll help you a lot. You're gonna see it pop up a ton. Let's try going the other way. X to the 1/9 power, well, denominator was 9, so I know I'm taking the 9th root of x to the first. X to the 1/9. And do I really need this one? No, I'll probably just write the 9th root of x. Similarly, how about the 5th root of b squared, if we're putting that one in radical form? The 5th root of b squared, 2 over 5, so the 2 goes on the inside, the 5 is the index of the root. And just a couple more, 3xy to the 4th, but then we're taking the 7th root of that, parentheses, 3xy to the 4/7 power. Then finally throwing a little bit of a curveball at you for a couple reasons on this last one. 16 to the negative 1/4 power. First curveball is, what is this negative? What is a negative exponent? Well, if you remember when we were going over some exponent rules, a negative exponent, I'm going to write it over here first. This is just like 1 over 16 to the positive 1/4. If you remember, that negative exponent flips where it is in the fraction. So instead of it over 1, it's 1 over it, 1 over 16 to the 1/4 power. So that negative exponent will commonly drop it down to the bottom of the fraction. So what does that mean for a radical form? Well, that would mean 1 over the 4th root of 16 to the first. And I'm not going to write the 1. Okay. That doesn't look bad. I mean, we did convert it to radical form, but there is a radical in the denominator, which in 7.5, we talked a lot about we don't want that radical in the denominator. So there are a couple things we can do here. We could multiply 4 times to get a group of 4 there. But there's also something we're going to start looking for when we start simplifying these expressions. Because what is 16? 16 is 4 and 4. Each of those 4s is a 2. Do we have a 4th root? The answer is yes. The 4th root of 16, we have a group of 4 there. That's what I meant to say. This is just 1 over 2, actually. And this is something we're going to start doing. Anytime we see a number in that radical, we can kind of see if we can just simplify it. The 4th root of 16, what times itself 4 times equals 16? 2. We found that group of 4, nothing left over. This is just 1/2. 16 to the negative 1/4 power is a very fancy way of saying 1/2. Now, if you are looking at it and saying, hold on, 1/2 doesn't have a radical in it, is that really radical form? I mean, I guess you could make that debate. I would say yes, we put it in radical form and then we simplified it, especially because we don't want that radical on bottom. So I'm going to go with yes, that's good. So this first stage should be kind of review. We've talked about this before, switching back and forth between rational exponents and radical form. But we're going to see, sometimes we're going to have just numbers, and sometimes we're going to have expressions with variables, and we want to be able to simplify and solve and do all sorts of things. So look at this problem, and I'm going to work it 2 ways. I want to show you both ways that we could do this. This says, what is 8 to the 2/3 power? 8 to the 2/3 power. Well, there are a couple different ways, as I mentioned, we could do this. If you think back to our exponent rules, we could say that this is 8 squared to the 1/3 power. We could say it's 8 squared to the 1/3 power because power to a power, if you remember, we multiply those exponents. So 8 squared to the 1/3 power. 8 squared I know is 64. I'm just going to go through and kind of start simplifying. And 1/3 power of 64, well, maybe I'm not quite familiar with 1/3 power yet, but I bet if I did this, okay, so 3 on bottom, 64 to the 1st power, I bet you would recognize it. Oh, it's a cube root. The 1/3 power is a cube root. Just like 1/2 power is a square root, 1/3 power is a cube root. So what is the cube root of 64? 8 and 8. So that's gone. This is 4 and 2, 4 and 2, 2 and 2, 2 and 2. We're looking for groups of 3. Group of 3, group of 3, nothing left over, so I can pull 2 2s out. So it looks like the cube root of 64 is just 2 times 2, or 4. 8 to the 2/3 power, judging by that, is just 4. So I just want to talk through and walk through what I did one more time. I separated out that rational exponent into 2 different exponents. I said, let's do 8 squared first. And then I'll take the cube root of that. So I did 8 squared is 64. And then the 1/3 power is the cube root. So I broke down 64, looked for groups of 3. 8 to the 2/3 is just 4. Not the only way to do it though. What if I said, well, I still want to split it into 2 exponents, but maybe I will do the 1/3 power first and then square it. Again, power to a power gets multiplied. That will be 2/3 when all is said and done. But we're just doing this in a different order. I'm going to put this into the more familiar radical form. What is the cube root of 8? 8 to the 1/3 power equals the cube root of 8. 8 is 4 times 2. That's 2 times 2. So we have a group of 3, nothing left over. The cube root of 8 is just 2. And 2 squared, you guessed it, will give us 4. So whenever you see a rational exponent and you're trying to simplify, you can always break it into two different exponents. You can say, do I want to do the numerator first? So like on top there, 8 squared, and then take the cube root. And that's just breaking that rational exponent into 2 steps. Or you can say, I'm going to take the cube root first and then square whatever I got. I typically, I mean, not all the time, but the majority of the time, I would do the root first. And here's why. Because 8 to the 1/3, well, that makes it a smaller number. That makes it 2, and then it's just 2 squared. Versus 8 squared first up top, then we had to break down 64, slightly bigger. Wasn't a huge deal in this case. But I think root first oftentimes helps us find the smaller numbers, and then we square, then we cube. So it makes our problem a little bit easier. I would be kind of irresponsible though if I didn't show you something. And this only really works for numbers. But can we check our work or perform this calculation with our calculator? The answer is yes. I'm going to say 8, and then the little caret, 8 to the 2 divided by 3. And sure enough, it equals 4. So you might be saying, wait a second, why did we just spend these minutes learning how to do it by hand if our calculator can do it? I'm going to show you. Calculator only works for numbers. That's where we're starting out. That's where our next few examples will be as well. But once you start getting variables in there, you need to know kind of these techniques. So hang with me and keep working some of these. So these 4 problems say rewrite and solve. I'm going to do the first one. And then I'm going to let you do the second one, work on it, and then we'll come back. So 16 to the 3/4 power. I mentioned earlier, I typically like to do the root first. So I'm going to say, well, that's 16 to the 1/4. Do that denominator first, and then cube it. So to the 1/4 is the 4th root, 16 to the 1st, and then the 4th root of that. Cubed. So if I know what 16 to the 1/4 is, the 4th root of 16, if I know what that is, I can just cube it and I'll be done. 16 is 4 and 4. 2, 2, 2, 2. There's my group of 4. So the 4th root of 16 is just 2. 2 cubed, 2 times 2 times 2. So 2 times 2 is 4. Times 2 is 8. 16 to the 3/4 power equals 8. Didn't need a calculator. Did it by hand. We can check our work with a calculator. So let me come over here and say 16 caret to the 3 divided by 4th power. And sure enough, it equals 8. So what I will have you do is pause the video and take a few minutes. It'll take you a few minutes, but try these next 3 problems. Now, if you're looking at that third one overall, the middle one of these 3, there is a negative exponent. I'll give you a hint, and then I'll let you just get started on it. Remember that the negative exponent makes it 1 over the positive version, if you will. So pause your video, take a few minutes, work these out as best you can, and then come back and check how you did. All right, now that you've had a chance to work on some of those problems, let's work them out together. This first one that I'm going to be working with, the 243, great example of, I probably don't want to cube 243 and then look for groups of 5. That would be a huge number. So instead, I think I'm going to try to take the root first, 243 to the 1/5, and I'll kind of keep it consistent the way I've been doing my parentheses, and then cube it. So look for the 5th root of 243 and then cube it. Because then the 5th root hopefully will help us get down to a smaller number, more manageable. So I'm going to come over here and say 243. I can tell 2 doesn't go into it evenly because it's not even. Maybe 3. There we go, 3 times 81. So 3 times 81. 81 I know is 9 times 9. 9s are both 3s. We have a 5th root. We're looking for groups of 5. And sure enough, 3 to the 5th power happens to be 243. So the 5th root of 243 is just 3. So really, my final answer will be 3 cubed. 3 times 3 is 9, times 3, 27. 27. We'll go ahead and check our work. 243 to the 3/5, 3 divided by 5 power 27. There we go. Hopefully that one went well. Let's look at this negative exponent one, a little bit different. But I gave you the hint before we paused that 27 to the negative 1/3 power is just 1 over 27 to the 1/3 power. That negative just means it's on bottom. So I'll stay true to form and say, well, 27 to the 1/3. And since that numerator is 1, I mean, I could put a 1 out there. I'm going to go up so you see my comparison. 243 to the 1/5, and then I cubed it because that was the numerator. 27 to the 1/3, but really 1/3 was what I was asking all along, right? So all I need to do is find the cube root of 27, find a group of 3, simplify that 27, and then it's 1 over whatever that is. So I'm going to come over here, I'm going to say 27, I'm looking for the cube root, groups of 3. 3 and 9, 3 and 3, 1 over the cube root of 27 is 3. 1/3 overall. So 1/3 overall, let's make sure 27 to the negative 1/3, 0.33333. And hopefully you recognize that decimal as 1/3, but if not, we can hit the math button and then say, turn that into a fraction, and it says 1/3. All right, 64 to the 2/3 power. I don't want to do 64 squared. I would much rather 64 to the 1/3, find the cube root, and then now that it's a small, easy number, I can square that. So 64 to the 1/3 squared. And again, we do have these tools. I've been showing you by hand because maybe you're taking a test that doesn't allow you a calculator. Maybe you're just calculators across the room and you don't want to get up and get it. It's good to know how the calculator does these things. Calculators are great tools, but being able to work things by hand is also awesome. What if I just went 64 to the 1/3? Oh, it tells me 4. 4 squared, I know that's 16. 64 to the, oh, that's a divided by, to the 2/3 equals 16. So with just numbers, here's what I wanted to emphasize in these 4 examples, and hopefully you had some success with them when you paused. Almost always do the root first. Do the root first, do the denominator. So 16 to the 1/4 first, and then cube it. 243 to the 1/5, then cube it. 1 over 27 to the 1/3. So find the cube root of 27, and that's just 1 over that. 64 to the 1/3, and then square it. We can break it up into those 2 steps because of our exponent rules. However, a lot of the problems we look at won't just be numbers. They won't just be numerical. And so this is where it gets a little bit, it's not complicated, I mean tricky. Here's kind of the hard part about this portion of this lesson. We have a lot of skills and we have a lot of bits of knowledge, and we could go off in 10 different paths, and we kind of need to know and recognize what path should I go off on this problem. And so I'm going to be demonstrating some of those common paths, common techniques to simplify these rational exponents. You can see on the screen I have a few general rules. Use previous exponent rules. We studied exponent rules, and it's important that we know them. That was chapter 6. We can still use them even if the exponents are fractions. Include only positive exponents. So in general, for the way our textbook is defining these, simplified means only positive exponents, no negatives, kind of like you see down here. We'll have to get rid of that negative. And any exponents in the denominator must be positive integers. In other words, rationalize the denominator. And I'm going to demonstrate what that means, why that is, and I think you'll see it pretty quickly after one example. But to start now, if I want to know x to the 1/5 times x to the 7/5, well, yes, those exponents are fractions, but remember, we actually know an exponent rule that can help us out here. I'm going to make up a problem for just a second to remind you of that exponent rule. 2 to the 7th, sorry, x to the 7th times x squared is x to the 7 plus 2th power, or x to the 9th power. When we're multiplying the same base and they're raised to some exponents, we just add those exponents. So putting that in the context of this problem, x to the 1/5 times x to the 7/5 would be x to the 1/5 plus 7/5. And fractions, okay, but they have a common denominator, so we don't need to find that. We just add them together. X to the 8/5 power. Just using our previous exponent rules. Nowhere in those rules did it say it wouldn't work for fractions. What about y to the -3/4? Okay, well, we can't have negative exponents. We were told it's include only positive exponents. So here's what I'm going to do. I'm going to do what I did above and say, okay, well, I got this. 1 over y to the +3/4. And that's now the negative exponent is taken care of. Now, rule 3 above. It says in the denominator we can only have positive integer exponents. Here it's positive, but it's 3/4. It's a fraction. Why is it a big deal that we can't have a fraction power in the denominator? Well, what happens if I convert this into radical form? No rats in the basement, right? We have a radical on bottom. We can't have a radical on bottom and call it simplified. So we need to get rid of that 4th root. Now the good news is we're almost there. Look, we have y cubed down there. We have 3 y's. It's not yet a group of 4, but it's not that far. I'm just going to multiply, kind of like 7.5. I'm just going to multiply by the 4th root of y. Because now how many y's do I have down there? 1, 2, 3, because it was a y cubed. 4, now I have a group of 4. That'll cancel out my y to the 4th. So I'm going to show a couple steps. Equals 1 over the 4th root of y to the 4th. What is the 4th root of y to the 4th? And you might be thinking, oh, it's just y. Kind of. Be careful. Be careful. Because it is just 1 over y to the 1st power. But do you guys remember, if we go from an even power inside the radical to an odd power outside, what do we need? We need to say 1 over y inside absolute value. 1 over the absolute value of y to make sure we are getting that positive principal root. And this is part of what I mean when I say things are going to start getting a little bit tricky, because what happened here? We had to remember how to handle a negative exponent, put it on bottom. Then we said, okay, translate it to radical form. Then we had to use our nth root knowledge to say, okay, we need to multiply by another y down there, a 4th root of y, I should say. And then finally, after all of that, and we think we're like there, we say, wait a second, we went from y to the 4th inside the radical to just y to the 1st, even to odd. We need that absolute value. And so I'm just gonna adjust this so it doesn't look like it went into the fraction bar. 1 over the absolute value of y. Now, I actually, sorry, I'm really tired. I totally messed this up. No, 1 over that. When we're multiplying, we have to multiply the same thing top and bottom, right? I don't know what made me do that. So hopefully you were at home screaming at me there. Hopefully you were saying, no, we can't do that. So I apologize for making that mistake initially. 1 times the 4th root of y. We have to multiply on top and bottom to keep things the same. So the 4th root of y over the 4th root of y to the 4th. Bottom stays the same, but it's just the 4th root of y. So I apologize. And again, right there, we'd better multiply by the same thing top and bottom, because that's just a fancy way of writing 1. That's keeping it the same. We're not changing our value. So the 4th root of y over the absolute value of y to the 1st. Okay, I will try to be a little more careful on these next problems. So here's our common technique I'm going to show you. Because half the time we look at this problem, we say the 8th root of 81 over the 6th root of 3. Like what? How do we simplify those? I mean, they're different radicals, they're different insides, radicands. So how do we simplify this? Oftentimes, we'll convert this into exponential form and use our exponent rules. Here's what I'm looking at. (81 to the 1/8 over 3 to the 1/6). Now, I hope you're okay with that step. And you might be saying, well, yeah, I'm kind of okay with it, but I don't see how that helps us. You're right. I'm with you. But can we write these different radicals into the same base now that we have it in exponential form? In other words, what if we expressed 81? I'm gonna come up here and well, I'll go down here. 81 is 9 and 9, 3, 3, 3, 3. I like this because it's 3 to the 4th, and that's kind of nice. 3 to the 4th, I'm rewriting my 81 to the 1/8 over 3 to the 1/6. Now it's looking promising because it's 3 to the something over 3 to the something. We can use our exponent rules if it's the same base. I'm going to use one of my exponent rules, power to a power. 3 to the 4 times 1/8, so 4/8, which is just 1/2, I can recognize, over 3 to the 1/6. So 3 to the 1/2 over 3 to the 1/6. And then one more exponent rule. When we're dividing, we subtract those exponents. Hopefully you remember. So that would be 3 to the 1/2 minus 1/6. I'm going to get myself a common denominator. 1/2 would be 3/6. So 3 to the 3/6 minus 1/6, which equals 3 to the 2/6, or 3 to the 1/3. 3 to the 1/3 power. Now there are a lot of steps there. And the good news is it's really nothing new. The bad news is it's a lot of old stuff and you got to know it all. That's why it was so important to memorize and really get solid in those exponent rules in chapter 6 and how do we convert and how do we simplify roots and all those things we've been working on. So I looked at this, I said it'll probably be easier to work in the middle if I can use exponent rules. So I switched it to exponential form. And then this blue step is the key. I rewrote 81 as 3 to the 4th. Now I can just use my exponent rules all the way because I have a 3 on top, 3 on bottom. So 3 to the 4/8, so 3 to the 1/2 over 3 to the 6th. Exponent rule, subtract 3 to the 3/6 minus 1/6. I made that a common denominator. Gives me 3 to the 2/6 or 3 to the 1/3. Now this is pretty good and you could probably circle this answer and call it good, but I like to live by just this one rule. If they give me the problem in radical form, I'm going to give my answer in radical form. In general, that seems just polite. That seems like good form. So I'm going to change this to a radical and say this is 3 cube root of 3 to the 1st. I don't really need the first there, so cube root of 3. And that's how I'll do this one. So you'll see this on your homework. You know, you got radicals and you don't have a common base, a radicand or a base when you're in exponential form. So instead, you will just do this. See if you can rewrite oftentimes usually the larger one, into the same bases below, and then use exponent rules. What about another common technique? Another common technique is, can I write what's inside of the radical? Can I write the radicand to the same power and simplify? Let me demonstrate what I mean by that. I'm looking for the fourth root here. The fourth root, 9 is 3 and 3, so I don't have any groups of 4 there. And z squared, I don't have any groups of. But it is true that this is the fourth root of 3 squared times z squared, right? 9 is 3 squared. And I could even write it like this if I wanted. 3z quantity squared. So the fourth root of 3z quantity squared, if it's not quite apparent what to do now, I would switch it to exponential form because we have all those exponent rules. This is 3z to the 2/4 power. And now I bet you see it. You say, well, that's just 3z to the 1/2 power. And so by writing the inside, the radicand, all something squared, now I can use that squared and the fourth root and simplify what root I'm taking, which is always a good thing when we're simplifying. 3z to the 1/2 power. If you remember, what is that 1/2 power? Square root. Okay. I want you to look at what we just did, pause the video, and try this one at the bottom of the screen. The fourth root of 100, a squared, b to the 6th. So you're going to see if you can write that entire radicand as the same power, something all to the same power, and then simplify using exponent rules. Pause your video. I'm going to pause my video, work this out, and then we'll come back together and see what we got. All right, we are back, and there you have it. This one was a little trickier. I mentioned we wanted to try to find something we could write the entire insides to. So first thing I did, I said, okay, so 100 is 10 squared. That's kind of nice. And we have a squared. We have b to the 6th. Okay, we can't write it as something to the 6th, obviously, because there aren't enough 10s or a's, but could we write it as something squared? And so you'll notice on this line that I'm starring, the fourth root of 10ab cubed squared. And if you think about it, 10 squared gives me 100, a squared gives me a squared, b cubed squared, and this was kind of the leap, b cubed squared is what would give me b to the 6th. So I was able to write the entire insides as just a whole thing squared, and then that let me use exponent rules. That means that whole thing to the 2/4, since it was a fourth root. Simplify that, it's a 1/2. And then just for good measure, since the problem was given to me in radical form, I ended it in radical form as well. So another example of that, and it's hard to know without lots of experience just where to go on these problems. And that's why this practice is going to be so crucial, just so you get that experience and start seeing those patterns. Got one more problem for us today, and that is this. Common technique, rationalize the denominator, m to the 1/2 minus 1 over m to the 1/2 plus 1. Now you cannot, and I can't stress this enough, you cannot just do that. In order to divide something out, it has to be present in every term. And there's no m to the 1/2 in these ones, so we can't do that. What can we do though? Well, I'm gonna do one step, and I think you'll see immediately. If we change those to radical form, we immediately see, shoot, we have a radical in the denominator, rat in the basement. So I know I need to multiply by its conjugate. This was last section, right? This was 7.5. Before I do, I like to write it how I'm used to seeing it in that order. -1 plus root, sorry, that was plus root m, because it was a positive root m and a -1, over 1 plus root m. And so what do I need to do? I need to multiply by the conjugate of the denominator. We've seen that before. 1 minus root m, just change the sign of the radical part. Multiply on top and bottom, not like my earlier example. And then we're going to FOIL and simplify. Now, again, I would love for you to just pause it, see if you remember 7.5, see if you can work this out and simplify it all the way. I will do the same, and then we will chat. All right, let's take a look at this last problem. We left off saying we need to multiply by the conjugate of the denominator. So I flipped the sign of that radical part. And from there, we FOIL. Could get a little bit tricky with all those negatives and radicals floating around. But on bottom, we see those radicals do cancel out. It looks like we get -1 plus 2 root m's minus m on top over 1 minus m on bottom. And then again, I like to, if my problem was given to me in exponential form without radicals, that's probably how we should return our final answer. So I changed that square root of m to m to the 1/2. So no radicals now. And then maybe one last step even. I might just write it in descending order. -m plus 2m to the 1/2 minus 1 over -m plus 1. And that's looking like a really nice answer. No radicals on bottom, no fractional exponents, right? There is one on top, but that's okay. It's simplified. We gave it back in that rational exponent form that it was given to us in. I'm feeling good about this answer. So in all honesty, this is a really tough section to master because we know how to rationalize the denominator. That's from 7.5. We know how to simplify square roots and we know how to use exponent rules. But the trick here is knowing which of all these skills should I use on which problem. And the only way to get good at that is through experience and just practice, practice, practice. So that's what I'm going to ask you to do. You've got some practice problems to work on for this. This is one of the harder assignments in the year, not because the calculations are so crazy and big numbers and such, but because it's hard to know where to go. Do the practice. Let me know if you have questions. Bring those questions to class so we can talk about them as a class. Most of these problems go fairly quickly, but it's just how do we get started? And that's the biggest issue. So take some time, do these problems, do them again, do some extras that I didn't assign. And then next time we talk, hopefully you will be bringing up any questions that you have. So that's it for 7.6. Hope it makes sense, hope it helps, and take a look at those problems and let me know how it goes.